In this highlight video, we will learn to relate intermolecular forces to trends in physical properties such as boiling point, melting point, and solubility. Boiling point is the temperature at which molecules are converted from liquid into gas. As the temperature increases, the heat supplies energy to break the intermolecular forces of the liquid, allowing molecules to escape into the gas. The stronger the intermolecular attractions, the higher the temperature that's required to allow a molecule to boil. Let's look at this series of alkanes. If we go from left to right, what type of intermolecular forces do we think would cause changes in boiling point? Well, these molecules are all very nonpolar, so the only thing that will really change are the van der Waals interactions. Like we said before, as the surface area becomes bigger, the van der Waals interactions increase. So we would predict then that we have stronger interactions on the right, weaker on the left, and so the boiling point should increase from left to right as those attractive forces increase. So let's write out what the actual boiling points are. I'll write them up above here in degrees Celsius. If we start with methane, this has a very low boiling point of minus 162 degrees Celsius. Ethane is minus 89, minus 42 for propane, 0 degrees for butane, to 36 for pentane, and 69 degrees for hexane. What can we learn from this about the physical state of these molecules if we're at room temperature, which is around 25 degrees Celsius? All right, so that is right here. So if we look at the molecules that are below that, it means that at room temperature, the temperature is above the boiling point. So all of these molecules going this direction will be gases at room temperature. Above this, these temperatures are above the boiling point, and so these have not yet converted to gas. These will all be liquid. As we will add additional types of intermolecular attractions. So let's just fill in what we already learned here. This would be 36 degrees, this is 69, and butane was 0. What happens when we add different functional groups? Each of these functional groups has essentially the same number of heavy atoms, so carbons or non-hydrogen atoms, as does pentane. So that's the one that we'll compare with. So if we go from pentane down to this is called chlorobutane, what would we expect to be the change in its boiling point? Well, we add chlorine, so it's going to add some dipole interactions because chlorine is more electronegative than carbon. So as we add these dipoles, we would expect the boiling point to go up, right? And in fact, the boiling point of chlorobutane is about 78 degrees Celsius. What if we go from chlorobutane to bromobutane? Okay, now we have a bromine instead of chlorine. Well, bromine is one level down on the periodic table, so it's bigger, and so the bromine is more polarizable than is chlorine, and that polarizability increases the van der Waals attraction. So we would again expect the boiling point to go up, and in fact the boiling point of bromobutane is 101. Okay, let's continue on. What if instead of having this straight chain of carbons, we have it all branched like this one on the right? Okay, in this case, we'd expect there to be less surface area. Right? And what's that going to do to the van der Waals attraction? And so the van der Waals should go down. Okay, and so the boiling point should go down. And so the boiling point of this compound is only 73. All right, so let's go down here from chlorobutane to this is an aldehyde, remember? Okay, we should add more dipole-dipole interactions, or have similar dipole-dipole interactions. And so the boiling point of this aldehyde is 76 degrees, which is similar to the chloro compound. What about if we go to the alcohol? How's that going to change the intermolecular interactions? Well, at this point, we've added a new type. We've added hydrogen bonding, right? Because the OH can have hydrogen bonding. And so we should expect then we have a stronger intermolecular interaction. The boiling point should go up. And the boiling point does jump up to 118 degrees. And if we add another alcohol, we add double the amount of hydrogen bonding. And so we should expect the boiling point to go up even higher, and it does 214 degrees Celsius. All right, let's look at a last functional group down here. Let's look at the amines. Okay, I'll just write out the boiling points and let's see if we can understand why they follow in this order. Each of these has the same number of carbons, nitrogens, and hydrogens. They're all simply constitutional isomers. Okay, so this one has a boiling point of 78, which is actually similar to the aldehyde and the chloro compound above. But if we put the nitrogen in the middle, the boiling point goes down to 55. And if we have the compound on the right, the boiling point goes way down to 36. Okay, so why would this be? All right, well, it has to do with the amount of hydrogen bonding. So the compound on the left has 2 NH bonds, all right? And each of those can hydrogen bond. The one in the middle has only 1 NH, so it has half the hydrogen bonding. Notice the compound on the right has no NHs. So this can do no hydrogen bonding. All right, and so as we look at this, the intermolecular attraction increases as we go from right to left as we increase the number of hydrogen bonds. Melting point is the temperature at which molecules are converted from the solid to the liquid. Okay, there's a slight difference here in that the solid is typically a crystalline solid, and so there's some crystal packing forces that are different than we see from going just from the liquid to the gas. All right. In general, though, melting point trends follow the same as do boiling points that we already found. So in general, the stronger the intermolecular attractions, the higher the melting point. The difference comes in is when we have isomeric compounds with the same functional groups, if they're more symmetrical, they have a higher melting point, and that's because the symmetrical compounds more easily pack together into a crystal structure. So let's see if it follows the same trends here. So the chlorobutane has a melting point of minus 123 degrees Celsius, right? Like with the boiling point, when we switched from chlorine to bromine, we saw an increase, right, to a higher temperature. So the melting point of bromobutane is minus 112. When we were talking about boiling points, when we went to this very branched compound, we saw the boiling point decrease, right? Because there was less surface area, and so there was weaker van der Waals interactions. In this case, we see that the melting point goes much higher, right, instead of going down. So this is something that's different, and this has to do with the added symmetry. Okay, so that was something different. So let's go down to the aldehyde below. Minus 96 degrees. As we add an OH, we have stronger hydrogen bonds, so this does go up slightly. It takes slightly more temperature. And as we go to this dialcohol here, minus 27. So all of these, except for this one, followed the same trends that we saw when we talked about boiling point. The last physical property that we're going to talk about is solubility. And so solubility refers to how well a molecule, which we could define as the solute, will dissolve in a solvent. Okay? In order for a molecule to dissolve, the intermolecular interactions within the pure solute must be replaced by interactions between the solute and the solvent. All right, and we follow the general trend that like dissolves like. All right, so molecules that are very polar dissolve in polar solvents. Non-polar molecules dissolve in non-polar solvents. Our molecules and solvents can be described as either being organic soluble or being water soluble. Okay, organic soluble is going to be non-polar, and those solvents are going to be things like hexane or maybe halogenated solvents. In the book they talk about carbon tetrachloride. That's not used so much anymore because it's carcinogenic, but dichloromethane is a common one. And polar solvents are usually things like water or maybe alcohols, but we're going to talk about organic soluble or water soluble. All right? Let's look at these four molecules that I have listed here, and we're going to categorize them as either being water soluble or organic soluble. Okay, we're going to start with hexane on the left side. Hexane is very nonpolar, and so it's going to be insoluble in water. So let's write this as no. And essentially the situation here, we could think of hexane as being an oil, and we have water, so this is similar to just oil and water. Okay, we're familiar with that. And so the nonpolar compound would definitely dissolve in an organic solvent. If we add an alcohol, okay, like this, we split the molecule into two ends. We have an end where the OH is. This is very polar. Or what we could call hydrophilic. That means that this part of the molecule loves water. The rest of the molecule, though, is more like an alkane. And so this is very nonpolar, which we could call hydrophobic. It means it's scared of water. All right? So it turns out that this molecule here would be kind of maybe partially water soluble, but it would dissolve in organic. All right, if we add even more alcohols here, right, that becomes even more polar. Okay, and now it's going to be water soluble and maybe not as organic salt. soluble. So final on here, let's look at two different alcohols. Let's look at this one here and this one here over on the right side. So now, notice we still have the hydrophilic part, but our hydrophobic part is much smaller. And so the hydrophilic part dominates this, and this would be water soluble, and it would probably also be organic soluble. All right, so this is a trend that we'll often see. So if we compare these alcohols, they have a hydrophobic end and a hydrophilic end. As we start with very small alcohols, they will be very water soluble. Ethanol is in alcoholic drinks, it is also fine in water. But as the hydrophobic end gets longer and longer, then it will begin to dominate the physical property, and that molecule will become more organic soluble and less water soluble. Let's summarize here on this slide. So if we start with molecules like alkanes, this one is called butane, we see that they are insoluble in water, soluble in organics. Okay, that's going to be always true. If we have a functional group that gives us a hydrophilic end to the molecule, they're going to be soluble as long as we have a small number of carbons. Okay, here they're saying less than or equal to 5 carbons per every oxygen. So we're going to kind of look at the ratio of carbons to oxygens, and if that's less than or equal to 5 to 1, then it will remain soluble in water. If we get more than 5 to 1, more carbons than that, like this one down here, then it becomes insoluble in water and is still soluble in organic. Okay, so this has kind of a cutoff here. That cutoff will be slightly different if we have alcohols or if we have amines, and we'll get a feeling for that as we move forward. So why don't you try to make a few predictions on some of these compounds here?